So first off, I'd like to invite up the next speaker, which is a joint presentation between Airbus and Altran. The speakers are Dennis Hahn and Mr. Max Seisler, and they'll be presenting on applications for print electronics in the aviation industry. Welcome up. Yeah. Welcome.
Hello.
Hi.
Thanks for having us. It's an honor.
Great. Thank you. Hi. Hi. Thanks. Over to you.
Wow. Good morning, everyone. For a research engineer, this is like Woodstock. This is awesome. Thanks for having us. My name is Dennis Hahn.
My name is Max Seisler. Hello.
And we are in a collaborative research project at Airbus and with Altran. And we're researching printed electronics for applications in aviation. Obviously, in aviation, we build aircraft. What you might not know is that in our smallest aircraft, we have about 100 kilometers plus of cables inside. That is 20% of which is just cabin, and the rest is the essential cables. However, 100 kilometers, that's like the distance from sea level to outer space, which is a quite impressive length for a small aircraft. Yeah, we will go through this presentation and show you a little bit about the general environment of aviation and the challenges we face as a research team. Then we go further and show you a little about what we do at the moment. And after that, I'll go a little more into details, what type of testing we do, and what kind of questions you have to expect from an aviation company to ask you guys when we get into contact and talk about future collaborations and or business. Max.
All right. So I guess all of you do know the passenger view from inside an aircraft, and what we want to show you today is the look behind what's into the technology and what's behind the cabin walls. So we're going to have a look first at manufacturing of an aircraft. So how does that look like today? And where's the reason? Why do we want to change something here? We're also going to look at the flight conditions, which are obviously quite extreme for an aircraft. During the lifetime, an aircraft does face very extreme maneuvers and climate conditions. And they do have a very big impact on the technology that we have in an aircraft. So next, we're going to show you where was the idea of the project born. So where does the technology come from, and which idea did we develop out of that? And we're also going to tell you where do we want to be in the next 5 to 10 years. So what's our roadmap here? We are also going to show you how far we have come so far. So we've done first prototype and product development, and we're going to tell you a bit about the messages and then the key findings we had here. To finally finish up with a chapter about certification, because before introducing any new technology into an aircraft, there's been loads and catalogs full of testing that has to be done, because safety is still the key requirement in aviation industry, and we want to make sure that before any printed cable is flying on an aircraft, the technology is mature enough and will be safe for the whole lifetime of an aircraft, which might be around 20 years. So to begin with, you do see the final assembly line in Hamburg. That's how it looks like when an A320 is produced. And obviously the aircraft has been a big success factor of Airbus. And in the development phase, late back in the 70s, no one would have imagined that today there's been around 7,500 aircraft produced. Like back then, people imagined that there would be a rate of 500 aircraft in total. So the production and the processes used here are focused on a production of a small batch, And what we do see is that the success and the huge need makes it a high need to increase efficiency in this production, because there's again another around about 7,500 aircraft that will have to be delivered in the next years. So having a deeper look inside, on the right-hand side you do see cable installation, and that's the topic we are faced. Because actually you do have a lot of cable inside an aircraft. Actually, you can say that we love cables a lot. It's been a proven concept, and to install those cables inside an aircraft, you do even bring more cables inside. And sometimes it does look quite complex, and it definitely is. So if you come up with a concept that promises you can make cable production more efficient, more flexible, and more cost effective, actually you will find a lot of people in Airbus supporting you, and that's what we've experienced here. So, talking about flight conditions, it's not only the maneuvers in flight that are extreme and extreme for the structure, it's also the climate conditions, because at the same time an aircraft can face temperatures of minus 40 degrees on the northern hemisphere in winter at night, and then in the afternoon can land in an airport in Dubai where temperatures may rise up to 85 degrees on the runway. So that's a quite huge range, and it's not just about physical conditions, it's also about the climate and many more factors. And Dennis is going to deep dive on that and the testings that have to be performed for that later. But now Dennis is going to show you where we want to be and where the project is leading us in the next years.
Yes, we made an illustration about that. So to understand that poster, it's not really hard to understand actually from what we are displaying here. The background information is quite the interesting one. The current status today is when our airline customers ask us to build them an aircraft, the customization process takes a couple of months. And it takes lead times in order to get all those electrical components customized. We develop the harnesses. The harness specification goes to a supplier. The supplier translates that into a building process, and then goes to somewhat like Mexico, and then the harness is manufactured in a couple of months, and then it's shipped back to Europe where we install it into the aircraft. Depending on the complexity, that the lead time can take all the way up to 12 months in order to get the harness delivered to the final assembly line, where we sometimes need 6 grown men to carry the harness into the aircraft and install that harness into the aircraft. With our concept, in a factory of the future environment, in an industrial IoT vision we have, we said this is no longer necessary. We will customize each and every cabin module, cabin element directly with the customer on an interactive surface, in an holographic environment, in an augmented reality, virtual reality environment. And once the customer is satisfied what he wants, either he wants the exit sign to read exit, or he wants that in Arabic or Klingon, we can make it then happen. We use this smart print button. Then the software develops basically the circuitry, and out of the circuitry another software develops the print layout that we need. We send this data stream to a multi-modular printer that is using the appropriate printing technology, dispensing, inkjet, screen printing, laser transfer, you name it. Picks and places the electronic components, precisely cuts out the substrate, cures the substrate and the components that are mounted on it, and then transfers it into a fully automated manufacturing of those cabin modules. then deliver it via AGV to the final assembly line where a smart robot installs it. And then finally, one of the Airbus blue colors is checking for form, fit, function, whether or not it is properly installed. In theory, we could reduce the lead times from 12 months to 6 hours. But that is just a theoretical value, so don't publish that. Well, the obvious reason we do that is we need to reduce weight. We need to reduce the part numbers. We want to reduce costs with that, and there will be a lot of labor costs reduced, and the lead time I already mentioned. But also, with this technology of printed electronics, we can introduce new functionalities. I will get into that detail a little later. The last-minute customization is a very common problem we have. Just recently, an airline customer, after this 8-month lead time for customized harnesses, decided to have a slight change. So we had to take the harness that was already delivered, chop that into 30-centimeter pieces so it does not appear on the black market, and we threw away 2.5 tons of aviation-grade cable material. Just because it was mentioned in the slide before. However, our vision is use this printed electronics technology and try to find quick win applications, how we can improve our current fleet at the moment, and we are exercising this with the info panel. We have that as a demonstrator here in the exhibition hall as well. In the midterm, once we got that aviation qualified, we will then disseminate this technology onto further applications to have bigger revenues with this technology in order to finance the long-term vision which you just saw on that poster. To go a little more into the details. The info panel. The right picture you see is basically the current status. We have somewhat around 128 parts. Those are assembled manually. It takes about 4.5 hours for a trained professional to manufacture one of those to be delivered to the final assembly line. So in theory, he can make 2 of those a day. So that means he can equip one aircraft, one A320 aircraft a day. However, we produce a lot more per day than just 1, like 2. No, we are aiming at 3 actually. But once we're done, we have the parts reduced to 10 only. We can produce that in a semi-automated process. And of course, with 126 parts we need to assemble, there's a whole lot of supply chain behind that. And we reduce that supply chain to an ink supplier, to a substrate supplier, to a conductive glue supplier, to an adhesive glue supplier, to a coating supplier, and some SMD supplier, but that is like bulk material. So a lot less than the other bunch we need. Say again? No? Sorry, misheard that. Yeah, and when we're done, it kind of looks like that. This is a concept demonstrator we developed earlier with the help of the Fraunhofer ENAS in Chemnitz. So the cool thing we do is we're planning the future of the next aircraft. It could be as much as a windowless aircraft because we would save a lot of weight. The structural integrity would be significantly better than with windows. And we would replace the windows by large area displays made of OLEDs, quantum dot, LEDs, or the next new thing. And we made a sidewall demonstrator of that, how it could look in the future. We printed an RFID antenna, picked and placed an RFID chip onto that, and it worked. We printed an OLED lighting system. Well, actually, we bought that off the shelf, but we contacted it with a screen-printed conductive line. We printed a gesture sensor, attached that to it, and so we can dim the OLEDs. And with a circular movement, we illuminate a LED strip that goes all the way around the display you see there. That's about 2.5 meters, and that we just did that to prove management that we can do the last meter, that we can do like 2.5, 3 meters with printed electronics easily, so our concept would work. But the real cool stuff we did was printing those sensors you see on the right side of that demonstrator. There are 3 temperature sensors and 2 humidity sensors. Well, all of you that are very familiar with the printed electronics technology say, why is that such a big deal? The thing is, for 500 grams, we can introduce 250 of those sensors throughout the aircraft. Compared to the 2 temperature sensors we have today, that is like a high-resolution picture of the climate inside the cabin. And with a smart air conditioning system, we could then install the perfect climate inside an aircraft. That given would reduce the chronic nasal and ingestion systems from the flight crews, because they have like typical dry sinuses. With that, they are very affected by colds, and with a cold you can't fly. So with this technology, we can actually reduce the need for the standby crew of an airline, and that is, we're talking real money here. So the airlines are really interested in us proceeding and being successful here. But in order to get that into the aircraft, there are some challenges we need to overcome. For one thing, there are the aviation certification authorities like the FAA, the EASA, and they have a specification, a requirement list that's collected in the DO160. That's like the requirements you have to achieve. Every item that flies, even the smallest, even the carpet in front of the lavatory, even the tiniest little thing inside the aircraft has to pass these tests. And then, of course, we have Airbus engineers who sign it off in order to say, okay, I'm responsible for designing that. So in order for them to sign it, they take the liberty to add some requirements. So usually the Airbus internal requirements and the Airbus internal tests are a little more tougher than the official ones. And then, of course, introducing a new technology, we need to show that over a lifetime it is reliable, it is safe, and it withstands a certain amount of chemicals that the item is introduced to throughout its life. So let's start out with the fiercest of all of them tests, fire, smoke, toxicity. Whenever you have a little demonstrator and you see the demonstrators in the exhibition halls, just imagine taking this little demonstrator and hold it for 14 seconds into a Bunsen burner's flame. When you take it out, the fire has to stop within 12 seconds. The burning depth shall not exceed 200 millimeters, and drops are not allowed. And further, smoke is only allowed in a certain minimal quantity, and the smoke is not allowed to be toxic at all. You can imagine if you work with a polymer substrate and have a silver ink on it, some SMDs on it, and a coating, and you burn that in a Bunsen burner. It took us quite a while to find the right combination, let's put it that way. The most funny of them all tests is fluid susceptibility. Because one would imagine, okay, every electronic device inside an aircraft cabin is introduced to condensed water and probably a little spillage of the trolley. However, that is not the case. With fluid susceptibility, of course, we test drinks. There's like the famous cola whiskey test, where we have like a bucket full of mixed fluids with Coke, with gin, with vodka, with whiskey, with Fanta, with tomato juice, of course, and that is all mixed up, and then it is poured basically over your electronic device. And your electronic device has to withstand that and still function after this fluid attack. Not enough. We also know that some airlines intend to clean their cabin, so the electronic device has to withstand a certain amount of aggressive cleaning agents. We do that with cleaning agents again. We mix them up in a bucket, pour that over the electronic equipment, and it has to work afterwards. The same we do with insecticides. As you probably experience when you travel to Australia, at the last stop in Asia, you usually have to get out of the aircraft, and then the whole aircraft is, I don't know the word really, but they use a lot of insecticides to make sure that no neocides are introduced into Australia. And electronic devices have to withstand those aggressive insecticides as well. Well, not enough, there's also the fungus test. Because in a moist, damp, sometimes cold environment, fungus tends to grow. So we put that into an ideal growing situation in a fungus-growing cabin chamber, and then we let it grow for 3 to 4 weeks, depending on the growth. And when you get your electronic equipment out of that, the fungus is about that thick over your electronic equipment. It has still to work, even though the fungus is really gross. So, but then of course, we do also vibration tests. There's a lot of vibration, and just in case of a turbine blade failure or an engine failure with turbine blade loss, you encounter a situation of windmilling. And once you YouTube the windmilling situation inside a cabin, you know what we're talking about with regards to vibration. Highly accelerated lifetime testing is a mixture of vibration, temperature, and also pressure, and humidity, I mean. And there we test it until it fails. And it has to achieve a certain amount of G forces. Of course, we do temperature testing, especially the survival testing is really hard for electronic equipment. We go down to -40 and go up to plus 85. Hold that for a couple of hours, and it doesn't have to work in those extreme conditions, but once it got back into a tolerance field of normal temperatures, it has to work again. Pressure is also a very big issue. You know that in case of the unlikely event of cabin pressure loss, the oxygen mask will fall from the ceiling and stuff. We know all that routine. However, going a little more into the physics of rapid decompression, that means a very small air pocket is all of a sudden a balloon. And it goes in a very rapid speed. So if there's a small air pocket underneath an LED that you mounted onto your device in a rapid decompression situation, this LED will get loose and it will travel with almost the speed of sound through the cabin. If your head is in the way, there will be a hole in it, and you don't want that. And of course, we don't want to pay for that either, so we make sure that this does not happen. However, humidity, you've seen the wet water landing already, and being around the equator, the humidity tends to get really high. And also having 200 people on board, just from exhaling, there's so much humidity inside the aircraft that it all condenses on the inner wall of the outer structure and is then absorbed by the isolation mats. And within 4 flight sorties of a short distance flight, within 4 sorties, you have accumulated around 300 kilograms of moisture inside the insulation mats. 200 of those kilos will stay there until the insulation mats will be replaced at the sea shack. Then, once we've done that, we do electromagnetic interference testing. As you know, that if you print something like that, if you have like a conductive track, that tends to work as an antenna, as a receiver, and a sender. And we have to make sure that this does not interfere with any primary flight controls. It does not interfere with any other controls. It does not disturb any data transfer which happens wirelessly in and around the aircraft. And also we have to check that in the unlikely event of lightning strike, that there will be no Lichtbogen? Arc. There will not be any arcing. And we're not done. We still have to test. And this is just actually just an abstract of what we do test. There's a lot more testing involved, actually. We do the extreme temperature testing as well with a lot of cycles and a lot of long days. Those long-term vibration testing and extreme temperature cycling testing, they can last all the way up to 7 weeks. And that only because we're allowed to test 30 prototypes in parallel, because we have to show that we simulate 130,000 flight hours without any significant failure of the equipment. And if we passed all that, then we do a mixed gas exposure, because in theory, around the lavatory, the sulfuric properties of the air is higher, the sulfuric compounds of the air around the lavatory is higher than in the other parts of the cabin. Sulfur basically interacts with silver, and silver is part of our conductive inks. So we have to test that. What effect does that have? Do we develop any dendrites that cause a short circuit? Do we have any degeneration in the conductive tract that might kill the performance of our equipment? But I will not bore you to death, because I will stop now with that. Feel free to ask any questions. Feel free to come by our booth. It's right next to the rear exit, and see for yourself what we did, and fire away.
Are there any questions? One here. James, could you pass the microphone?
Hi, thanks for the presentation. I have a question about certification. You mentioned in the beginning that you need to do all this testing, so I wonder if you can show up provide some light about what happened with the certification process in order to have the product flying.
I'm not sure I understood the question.
What happened after you do the test? How did you get the certification?
Well, we do have an official test report about every test, and this test report is validated by a certification validation engineer inside Airbus, and then it will be brought to the authorities, and they will have a look through the test reports and the validation engineer, and then they talk about it, and then they usually grant the qualification.
So how far are you in that process?
We're getting there.
Okay. Okay.
No, we're still in the testing phase, and we're still in the prototype adjustment phase.
Okay, thanks.
Thank you. I think we need to move on, but let's thank the speakers again. Thank you.
Thank you for having us.
For